go to that. Okie doke. It's about that time. Let's see, we got 1, 2, 3, 4, 12. 12. Okay. So, well, that was convenient of Jonah. That's the only one missing. Easy. Alrighty then. Okay, a couple notes. So homework, I used the journaling system. The main reason I did that for your uploads for your homework was I didn't actually want to assign points to each and every single homework in the end. It's worth 10% of your grade. I believe that's what it was. And all that. But for the most part, you get the points. Again, if you're doing your homework, if you're making real live attempts on your homework, you'll get 100% on that. And so, you know, I kind of hate to have it clog up the grade center, right? Because, I mean, there's a lot of homework, right? It's pretty much, you know, you really need to do a lot of homework in a class like this to just work on even things like motor memory with you know, it just, lots of practice is what you need. But I found that putting it in as a journal clogs up the files. So you don't see those, but if I go to content area, and I suppose, I don't know if any of you have ever done that, I'm sure you have a content area. But if you go to content area, this is just all the uploaded files and videos and all that you might have done in the course. Well, you know, it turns out that your journal stuff clogs up my content area. And so I'll probably switch to doing an assignment upload, but that assignment probably will have 0 points. Okay, and again, that's just so it doesn't end up overtaking the whole grade center. And you know, you're trying to look at a quiz grade and you got 25 homeworks you got to scroll through to try to figure that out. So so I'll probably just do it with no points and not have it show in the grade book, the homework part. Okay, if you know, and for the most part, you know if you're missing homework, right? Because you didn't do it and didn't turn it in. But if you ever have a question, you can always ask me. Yes.
Where were we supposed to turn that homework in?
Oh,
I've never seen a spot to turn it in.
okay. Good question. So come over here to Module 1. I haven't set up a folder yet for Module 2, but if we come to Module 1, right under the homework, so there was the homework, and then if you click that, homework submissions, you should find these journals, okay? And like I say, that they were journals that time, but now I think I'll probably just do them as assignments, and so you'll click on them and do them that way. But it'll be the same idea. I'll make a folder as a place you can turn them in. Okay, so, well, actually, I guess I just need to go to Module 2. And yeah, so on the module 2, I added the dates on these. And notice, so I went ahead and I thought, well, you had a bunch of stuff to turn in last night. If I made the first homework due tonight, it'd just piss you off, right? So, but we have 4 sections we're doing homework out of, and I think it's around 15 problems a section. That's kind of what I did. Now, that said, really, you should probably be doing 30 a day, 30 problems a day. I'm not going to assign 30 because when I first started teaching, I probably assigned around 25 or 30 a day. And people, on the whole, grudgingly did it. But over time, at some point, I just found that if I assigned that many, too many students just didn't even do one. It was like they looked at it and they went, oh, I can't do all this, so they didn't do any. Well, that's a bad idea. Over the years, I kind of waned it down to about 15. Now, but we have a lot more technology available and so forth. So, if you really think about those problems and think about the material as you're doing the problems and work on the project and all of that stuff, probably 15 is enough, okay? But it wouldn't hurt, I mean, if you have time to do extra, that's the hard part, but if you have time to do extra, not a bad idea. Go ahead and do some extra. It really is a good thing. Because there is a lot of skill to this, and I think anybody who's ever worked on a skill, whatever that skill is, right? Hammering a nail, hitting a tennis ball, throwing a bowling ball, well, rolling a bowling ball. I don't know, maybe you throw them too, I don't know. But any of those kinds of things, you practice it. You have to practice. And I think in some ways that's part of the reason I like math was I am a practicer. That's just sort of the type of person I am. And so it fits well with me. If practice is something you absolutely abhor, yeah, probably it's not going to fit as well with you, But if you get the idea of practice and so forth, I think it applies to mathematics very much. Okie doke. So we've got those due dates. I started tomorrow night. If you work on, you should start working on things today and all that. So if you get them done each a day early or whatever, that's fine. I took a look. I saw everybody's done the quiz, so that's good. I haven't looked at projects. I think I got 1 or 2 emails on those, but I haven't looked at that yet. And that's probably all on that I have right now. Questions about anything right now? Yes?
I have a question about homework exercise.
Okay. From last week or this week?
1.3.
1.3? Okay. So,
59.
number 59. Me either. Okay. Yeah, so let me mention a couple things and then we'll look at number 59. So we're starting limits, and just to make sure everybody's kind of at the same place. We're starting limits, and that idea, I think I mentioned it last Thursday, but you know, we're asking questions like, you know, what is the limit as, say, x goes to 3 of the expression or the function x squared plus 5? Okay? We're asking that question, and well, what the heck does that question mean, right? And so here's a graph of x squared plus 5. Whoops. Sorry about that, Nick. We'll get you back on there so you can see. He's, you know, he could probably hear the chalk and he's going, "Oh, turn it on, turn it," you know, something like that. But so yeah, we want something like the limit as x goes to 3 of x squared plus 5. And, you know, if I'm looking at that graph of x squared plus 5, it looks something like this. And so this notation, this language here, is asking, okay, if that's 3, I would like to know, as I come in this way from the left on x, and now, it's just kind of happenstance that that arrow and that arrow are pointing in the same direction, because I also need to know as I come in that direction. Okay, I'm asking, as x comes in here toward 3, what's happening on this graph? Or another way to look at it is, you know, what's happening on the y-axis, but it's much more, I think, intuitive and visual and so forth to kind of see, I'm going along this path, I'm coming along this path, and I want to know, where am I headed? Okay, I don't actually want to know where I end up. It's a very weird difference, but I want to know where I'm headed. Okay, so I look at this, and in this case, it's pretty obvious I'm heading right there. Okay, and so also in this case, it's pretty simple to evaluate this. So if I do, in this case, if I just say, oh, well, the answer is, well, all right, it's 3 squared plus 5, which is 9 plus 5, which is 14. Okay, what I just did here was direct substitution. Okay, in this class, for us, if you've got a really nice function like this and you can do that, that is the answer. That's how you figure it out. Okay, you just do direct substitution, you plug it in, you go, oh, there's the answer. Okay, but places we have to be careful are things like the limit as x goes to 0 of the square root of x. Right? Direct substitution, I put it in, I get 0. That was easy. Except, this is undefined. Okay, the reason it's undefined is, well, there's the square root of x. There's x equals 0 right there. Well, notice, you know, as I come in this way, well, I could say, yeah, I'm just heading down that path right there. Great, it looks like I'm heading to 0. Unfortunately, trying to come in this way, I have no path. Can't do it. Okay, so visually, what we, you know, as we look at limits, we are just looking at these graphs. 1.2 is pretty much this idea of looking either at pictures or at tables and just looking for the obvious. Okay, so so I just wanted to mention, 1.3, there's not lots and lots to do there in 1.3. Or sorry, 1.3, 1.2. 1.3 is where we have our question. 1.2, that's the visual and table stuff. So graphically, I am just truly looking to see, they're going to give me some x value somewhere, so there's x equals c, and I might see a picture, and that comes in like that, and this one comes in like that, and so now I can tell you the limit, and this is f of x, the limit as x goes to c of f of x is undefined. There you go. It's undefined. Now, they may give you the algebraic notation for a given representation and show the picture, in which case, if you were sort of lazy, you could maybe go to Desmos or something like that. But I also wanted to point out right away, and then number 59, we can kind of reiterate this idea. But you got to be careful about what we call removable discontinuities in these things for limits and Desmos. We don't hit continuity till 1.4, but suppose I'm looking at graphically, something like f of x equals x squared minus 1 over x plus 1, something like that. And I ask, well, what's the limit as x goes to negative 1 of f of x? So I'm given that, and I'm in this graphical section, and so I'm going to switch over to Desmos here. Desmos, and I just plug that in, and maybe I'll even say the f of x. So f of x equals x squared minus 1. And then if I highlight that whole thing and hit the slash, then I can do my x plus 1. And notice that if I zoom in here at x equal negative 1, right, it looks continuous. Or another, and now again, we don't hit continuity until 1.4, but the point is, to get this limit, wouldn't it be nice if I could just go here and click, and hopefully you can read that. Well, I'm off of it a little bit, right? When I hit that, I really have to look at it more like a table, because right there it says undefined, right? Because I can't divide by 0. If I went here and I said, well, let's try direct substitution, undefined, okay? But when you're looking at the picture, it doesn't look like there's a problem there, not until you're actually there. So in this stuff, be careful about that sort of thing, is that technology, what technology tends to do is it just connects dots. It evaluates the function at a few places and then draws straight lines in between it. But, it can use enough points that it looks like a curved line to you. Okay, but pretty much it just connects the dots, just like back in the days when you were little and did your connect the dot puzzles, that kind of thing. So that's that's what it does. And so in this case, you know, we could use the table approach. So if I grab this and I start sliding it, you know, I can see what the numbers are doing as the x value gets closer and closer to -1. You know, I see that the y value is getting closer and closer. It looks like to 2. Well, actually, -2. Right? So it looks like it's getting closer and closer to -2. And I could check that by doing some tables, something like that. Okay, but then in section 1.3, the idea is we can get away from all this stuff and we can use our algebra skills to get that -2. Okay. Again, 1.2, it's pretty much looking at the graph and looking at tables. The big idea, though, with limit is that we don't care what happens at the point. We care what happens in approaching the point. Okay? Because, again, you take something like this, and we've got that open circle right there. Well, I could define f of x to be, you know, maybe this is -2, that's 2. And so I could actually define this as a piecewise function and say this is x squared minus 1 over x plus 1 when x is not equal to -1. And, whoops, I did it again. Okay. I might get better at this at some point, but I don't know if I'd bet on it. Okay, so all right. So I'm letting Nick kind of catch up on what's on the board there. So we had our f of x, x squared minus 1 over x squared minus 1 over x plus 1. The limit as x goes to -1 of f of x. We said, yeah, that's -2. Now, you know, so here's what we would draw the picture. Forget the point for a moment. That's how we would draw that picture. You know, there's f of x, there's y. But I could define a piecewise function where I do this and then say that it's equal to 2 when x equals -1. I could do that. But in this case, well, actually, I should probably not use f. I should probably use g of x, because that was f of x over there. So here's g of x. But now, you know, if I say, what's the limit as x goes to -1 of g of x, well, that answer is still -2. I don't care how it's defined at x equal -1. I care what's happening as I'm getting there. It's all about the trip, not the destination. Questions on just this basic concept? You know, we're just looking at this thing called a limit. Okay. All right, so how do we handle this stuff? So I want to do just a little bit more with this f of x, g of x thing, and then we'll look at number 59. So in 1.3, where we use our algebra and we use some algebraic properties of limits, that sort of thing. What we use, you know, we can, and actually these are the problems that are most of most interest to us. Okay, if you can do direct substitution, great. There's the limit, you're done. I'm happy. Okay, but on something like this, I can't. So where you can't use direct substitution, we can put some theorems to use. And so if I would like to know the limit as x goes to -1 of x squared minus 1 over x plus 1, well, what I can try to do, and for most of our problems they give us, we've got really one of two things we're going to do. One is factor it just like I'm going to do here. The second is to multiply it out somehow or multiply it by something. Okay? But for the most part, it ends up coming down to this same technique pretty much every time, is algebraically, we hope to get to a position like this where it looks like, oh, I can just cancel out the x plus 1s. And then I can do direct substitution, piece of cake. Now, technically, you can't just cancel out the x plus 1s. Okay, it's not actually really working that way. Okay, because you end up with two different functions then. If I just get rid of those, then all of a sudden I'm saying, now it turns out to be true, but we don't know that at this point, is I'm saying, hey, you know, this function and this function x minus 1 are just the same thing as far as limits are concerned. Well, actually, as far as limits are concerned, yes, they are the same thing. They're going to have the same limit at every value of x. Okay, but they are not the same function. Right? If I get rid of those x plus 1s, I get a function that's defined everywhere, and this function is defined everywhere except x equal -1. So they are not the same function. So to be more careful about things and using our limit properties, what you're really doing, and it's much like working with fractions and all that, is you're really saying, hey, this is the limit as x goes to -1 of x plus 1 over x plus 1 times the limit as x goes to -1 of x minus 1. And the point is here, that limit is a no-brainer, right? Because if I go back to section 1.2 and I think of the graph, or if I think of a table if I made it, for this one, remember, I don't care what happens at x equal -1. I only care what happens as I'm heading there. Well, for every x value other than -1, that is 1. Right? So I get 1, 1. Everywhere I evaluate, I just keep getting 1. So I'm pretty darn sure the limit is 1. Now, we could go so far as to prove such a thing. We aren't going to. Okay? But that is, 1. And therefore, then I get 1 times, and that limit's really easy because I can do it by direct substitution, and I get -2, and so that's how I get my -2. So in this 1.3, this is the stuff we care more about. I mean, if you can do this, just the direct substitution, fine. We've got all these nice limit properties that say the limit of a sum or a difference is the sum or difference of those limits. Here we said we use the fact that the limit of a product is the product of the limits. Okay, so I had the limit of this function, x plus 1 over x plus 1, times that function, x minus 1. And I said, well, that's just the limit of this function times the limit of that function. So that's the kind of properties we get to use. And pretty much they work just like you would hope. Right? Adding and subtracting, we can break things up. Multiplying, dividing, we can break things up. Now, the key is, though, as long as all the limits exist separately. And these do, right? The limit of this thing was 1. The limit of that thing was -2, so we were fine. Division, of course, it can get bad because I might be dividing by 0. That would be a problem. Powers, we can do that. Composition of functions, again, if you've got a nice limit at the inside function and everything's defined nicely and so forth, you can get limits on the outside functions, and you can move that limit inside or outside. Those are all nice properties, and they're things, if I didn't tell you any differently, you would just do it that way. Not knowing that you could, you just go ahead and do it anyway, all right? They aren't weird rules or anything like that. They're the stuff you would hope would be true and are true. Okay, so along these lines, in 59, they want to know, now in this book, they start with this kind of notation, and they end up changing it at some point, I think. But they've got this delta x thing going to 0, and 2 times x plus delta x minus 2x over delta x. I think I have that. Yep. Okay, so as you're looking at a problem like this, pretty much these problems, when you see that delta x, yeah, it's probably going to be this type of thing. And if I do direct substitution, right, if I let delta x be 0, then I get 2x minus 2x, that's 0, divided by 0, 0 over 0, undefined. Now, 0 over 0, though, it's another quality other than just undefined. It's indeterminate. Okay? And by indeterminate, we mean, well, it might actually be something, but we don't know what it is. We haven't determined what that is. It's not clear what it is. And pretty much in the beginning of chapter 2, these are the limits we need to do. They all look like this. They're all 0 over 0, and we're trying to get rid of that delta x on the bottom. Now, probably at some point, even if the text doesn't switch soon enough, but I'm really sure it does switch at some point, I will start writing stuff like this as h goes to 0 of 2x plus h minus 2x over h. H is just way easier to write than delta x. And it's a typical thing mathematicians use instead of delta x. They use this small h. I'll do this one this way, but for now. But at some point, I'll probably start using h much more for this delta x idea. Sometimes, though, the delta x is a real handy symbol. Okay, again, this is a language. And in the language, choosing the right words is sometimes very important. And, here we have synonyms, right? But maybe that word is better than that one at some point. Okay. But if you're just kind of crunching through stuff like this, The H is just much easier and quicker to write, so it's nicer. Okay, so here, pretty much the strategy for all of these is I'm going to have to do something to the top of this thing to get it such that I can get that delta x to cancel with a delta x up there. You know, that's what I'm hoping is I can turn the top into something that has delta x in every term and I can factor it out. So as you do these, it gets really easy to forget to write, you know, limit as delta x goes to 0 in front of stuff, but you should write that until you do a direct substitution. And so now I'm just going to multiply that through distributive property. And so I have 2x plus 2 delta x minus 2x over delta x. And see, at this point, now, you know, I'm just using my usual arithmetic, algebra types of relationships. I can move stuff around up in the top here and say, well, I've got 2x minus 2x, so that's 0. And so I just have 2 delta x over delta x. And at that point, you see, now it's like this. I can factor out the delta x over delta x. At some point, yeah, I'll quit worrying about this little step in here. Early on, though, I think it's a really good idea if you try to remember doing that, okay? Because it can matter, okay? And it is what's really going on mathematically. And so I have my limit as delta x goes to 0 of delta x over delta x times the limit as delta x goes to 0 of 2. And so really, at this point, these are very much the same sort of limit in that this evaluates to 1 everywhere, well, except at delta x equals 0. But that's okay. We don't care about that. You know, we just care about what's happening on our way there. It's 1 everywhere. This one, it's the function 2, so it's 2 everywhere. And so I'll go ahead and erase this now. And so this is equal to 1 times 2, and we get 2. The big thing on this kind of stuff, so for instance, you'll get things like, so here's an example. F of x equals x squared. And they will then ask you, because really what's going on here is the function they were dealing with was the function 2x. And what they then asked was, hey, what's the limit? And I'll use an h in this case, as h goes to 0 of f of x plus h minus f of x over h. That's our big limit. That's a derivative. Okay, that limit is the definition of what a derivative is that we spend the rest of this darn semester looking at. So, you know, that's why they're having you do this is, oh, we just found that the derivative of the function 2x is 2. So there you go. We got our first derivative. Now here, you know, the thing is, here's what, well, should keep me awake at night maybe, but it doesn't really. Maybe makes me cry or makes my soul hurt or something. Is here, this thing, that's actually where most people screw up. just evaluating that. Okay, so this is the limit as h goes to 0. Now, this is f of something. Well, f of x, right there, everything gets squared. So you want to remember that the function is the squaring function, so that goes inside the squaring function, and then you square. So many times, you know, I'll see people write something like that. Well, that's not right. Okay, so, you know, just try it with, you know, here's 1 plus 1 squared. Well, that's 2 squared, which is 4. But 1 squared plus 1, so there's taking the x, that's taking the h, right? If I did it that way, right, I get 2. It's not the same, right? It's wrong. And so, you know, that tends to mess people up. Now, then minus x squared over h. Okay, so that's usually the worst part. That's where people just really screw up, is they just, when they get a definition for a function and then they're asked to substitute something more than just a single letter or a single number into it, often they mess it up. So just be really careful about it and really think about it. You know, what you can do on problems like this to help you out is that, you know, if you're given something like, oh, well, you know, f of x, well, we'll call it g of x, is, you know, like x squared plus 3x minus 2 over x plus 1, you know, actually put in the parentheses around the x, and then whatever, you know, you end up having in there, you just stick it in. But it's something that just people screw up all the time. And there's really no reason for it. I mean, you know, that's, we know what it means. I mean, you know, as I talk about it, for the most part, I think everybody's going, well, yeah, that's obvious. Yeah, but then you still do it, right? You know, I mean, so, you know, be careful about that sort of thing, and we'll get rid of that. Then, the next worst thing, of course, is when people don't, you know, do things like cube or square or something correctly. You know, make sure that you get the right answer here when you square things out. But that's what we need to do. So the limit as h goes to 0, so we get x squared plus 2xh plus h squared. So we have to write it out. If this was to the 10th power, guess what? You'd still have to write the darn thing out. You know, it's just, you just have to. And then minus x squared over h. But now, you know, here's where I've got my x squared minus x squared, which is just 0. And technically, I suppose we could even, you know, say that, well, you need to get that 0 and then move that out of the, you know, no. Multiplication is good enough. I worry about this step here. I don't worry so much about the idea of adding 0. That doesn't seem to be as big a problem for people. So here, you know, we get the 0, so we can get rid of that. And we're left with the limit as h goes to 0 of 2xh plus h squared over h. And so this is where our magic is, that now we have, you know, an h and an h. I can factor an h out of the top. That's the game. It's always the game. On these, we're always trying to do that. And so we succeeded in this case. we've got, this is the limit as h goes to 0 of h times 2x plus h all over h. And so now the limit as h goes to 0 of h over h times the limit as h goes to 0 of 2x plus h. And again, that's just 1, and this I can do by direct substitution. And so I get 1 times 2x plus 0, and so I get 2x. But in this section 1.3, this is the game. Pretty much whatever they give you, if you can't, if you can't do it by direct substitution, you'll probably have 0 over 0. Once in a while, you may get something that's an infinite limit, but I don't think in 1.3 they give you that, because there's a whole section 1.5 about infinite limits. So I don't think any of the problems are like that. Now, most of the problems, the problems where you have to do quite a bit of work are these where you start out, if you do direct substitution, you get 0 over 0. And then it's a big game after that. Now, I would like to point out that no, that's the guided project. So, in the instructional content, I don't remember so much here. Whoops, that's not what I want. Quit that. Come on. I don't know what you're talking about. You're having trouble with Blackboard. Working just fine for me. Yeah. I don't know what's... there we go. Finally. So in here... Oh yeah, I've got a couple videos where I go through some homework problems. But in here, in 1.3... and I just haven't gotten that far in 1.4 yet, but in 1.3, so I go through, some of the stuff in the text and the squeeze theorem and so forth. But then, there's exercise 7, 24, 29, 38, 44, 52, 56, 60, 88, 90, So I've got a lot of example problems in there for you to look at, because I knew, we don't have time to go through that many examples. And then I will do the same with section 1.4 and 1.5. I'll add some problems. Any other questions right now? I got one more thing to say, but I want to make sure. Questions? No? Okay. So I did, I haven't looked at, how things have gone for the first project yet, but second project. So last week and this week, kind of tight with the projects, one a week and so forth. But after that, every 2 weeks. So it slows down a bit after that. And your other courses, probably they didn't do a darn thing last week anyway, right? I don't know. Anybody taking organic chemistry? Yeah, you didn't do anything last week, did you? Yeah, so, I know, you've got other classes that are doing stuff too. So, but yeah, so, once we get through this stuff, and we're just kind of flying through, getting the ideas, then we'll slow down and go much quicker on the derivative stuff and all that. But yeah, so here's another project. In this case, I don't think it's near as many pages when you look at it, but here we're looking at the definition, so if you look at the title here, contextualizing the limit. One of the portions of this text is the definition of the limit, the actual formal definition of a limit. And it doesn't go, if you try to just teach it and tell you all, oh, you got to do these problems, it doesn't work. It's not a good thing to do that way. But if you think about what the limit is saying, it's merely saying that if I have a measuring process that composes or combines.
Excuse me.
Yeah.
Can I see the board, please?
Oh, good for you. Yep, that's what you got to do. You got to speak right up. Okay, so measuring, doing some sort of measuring process that composes or combines. By composes, I take one measurement that feeds into something else that also does a measurement or something like that. Or combines, I take these two measurements and somehow put them together, right? If you've taken chemistry at all, they've probably talked about, errors and all that kind of stuff. When you do that, right, actually the natural question is, if I want a certain error at the end of all this, I want to be this precise at the end, how precise do I have to be at the beginning? That is, I think, a really reasonable question. And actually, it comes down to, if you look at maximum error, which is what we're doing in this second project, when you look at it that way, it is the definition of limit. And so there's an application of this highly formal mathematical thing, is actually, how do you go about ensuring certain precisions in your measurements? And so that's what we're going to do in the second project, is ask that question. How would we do that for something simple, like, it's about as simple as we can get. I measure something and square it to get the square area, right? Or I measure both sides and multiply them together, but it really turns out to be essentially the same thing. Okay, so I just want to get the square area of something, but I use a linear measurement to do that. How good does the linear measurement have to be to get the small enough error on the area? That's what project 2 is. Okay, so I would call that very applied. Okay, but yet we're using a highly formal mathematical construct, or it mimics that. So with that, we are out of time. So I will see you on Thursday. And if you have any questions at all, shoot me emails, all that kind of stuff. All right, Nick. So sorry about that, but
It's all right.
we got you now. So
I did
all
have
right.
one question.
Yeah. Okay.
On the left of the blackboard behind you, how does the h turn into a 0 in the equation?
Because it's the limit as h goes to 0. And so at the point where we could actually do direct substitution. So see, if I let h equals 0 here, I've got a problem because I get 0 divided by 0, and I don't know what that is.
Oh, okay.
But after I evaluate this limit here and get 1, so I'm not actually ever putting in the 0 over 0 here, I'm just going, hey, if x equals a half, I get 1. I mean, sorry, h equals a half, I get 1. If h equals a tenth, I get 1. If h equals minus a tenth, I get 1, right? Everything's always 1, so I know that that limit is 1.
Okay.
And then this limit, I can do by direct substitution. Because I can just put
Okay.
the 0 in there and get the 2x.
All right, I understand that.
Okay, great. Anything else?
Thank you, sir. Actually, I was taking notes, and on the right side of the screen, in
Yep.
parentheses, is that x plus 2 squared?
Uh,
Let me see.
right here,
Yes.
that is x plus h squared.
Okay. Yeah, oh, yeah, that's what I meant. There it is. I was looking at the notes, but telling you what I wanted, but I was looking at the wrong note.
Okay?
But yeah, that answers my question.
Okay, great. All right. See you on
Thank you, sir.
Thursday.
Okay. See you later.